first thing that we discussed continuity equation. Okay, so in different forms, and we were trying to understand the momentum equations or less momentum equations. So here, momentum equations basically, if it includes viscosity as an aspect, it is called as Navier-Stokes equations. Okay. So people are joining still. 49 people are joining. So momentum equations. This is what we are trying to understand: the conservation of momentum. Okay. So basically, this is called as Navier-Stokes equation. Navier-Stokes equation. So if it is involving viscosity as a parameter, okay, if viscosity is included as a parameter, this is called as Navier-Stokes equation. So people are still joining. I have to admit that. Okay. So in some cases, you may think that viscosity is not an important parameter. So we can drop the viscosity term from the equation. And in such cases, the momentum equation is called as Euler equation. Okay, so viscosity is negligible. Okay, so these are the two ways in which momentum can be written. So I was trying to give you the notation in which you can represent stress. Okay, and from stress, you could calculate the forces acting based on the equation stress into area, okay, on which it was acting. So we were trying to understand this in perspective of a fluid element which was in motion, okay, we were trying to understand this in perspective of a fluid element which was in motion. And this fluid element is subjected to motion because of the force, which is the prime over the force, which can act in different coordinate axes. Okay. So people are still joining. Okay. So here I told you that for example, we can take the control mass approach if you want. So I was telling control mass and control volume approach both can be taken for finding the governing equations. So we are trying to understand this in perspective of control mass approach. Okay. And here we could understand that these forces can be of, this is mainly about surface forces we are talking about. Okay. The surface forces can be about shear force, okay, or they can be normal force. Okay. And then another category of forces can be the body force. Okay. And we were telling body force of type gravity, and then another type is field forces like magnetic field force. Okay, such forces can happen. So here in this notation, where we represent the shear stress, I was telling you it represents initially which the stress is acting in the direction J, and this stress is acting in a plane that is perpendicular to I. This is how the rotation is written. Okay, so with that we understood we could okay, we could represent the stresses like normal stress. Okay, and with this notation. Similarly, we could represent shear stress. Okay, with this notation. Similarly, you can imagine the stresses in all the different phases which it could act. So you can just imagine all the different phases in which it could act. Okay. So I was giving one just a simple example for it. Okay. So now with this stress being calculated, and you know the area on which it is acting because this area is available to you on which this stress is acting. So you could easily find the forces on each of the phases that is acting. So let me draw that one single figure which will represent all of this just before writing the final equation. I will not derive the equation because it will take a bit of time doing that. You can refer to any textbook and you can get it. But I'll just give you a hint on how this has been framed so that while you look at any standard textbooks, you will not be confused how this was obtained. I want to go to this the final equation just because it gives a lot of insight on what we learn later. Okay. Otherwise, we will never know why the equation is written in that way. Okay. So, in order to just explain that, I would just, I may need a detail of a fluid element, okay, which is under various forces on its axis, on its faces. Okay. So let me just write the various forces here. Normal force here. Okay. The normal force here. Similarly, the normal force here. The normal force on the other face. Okay. Similarly, the normal face force in this direction on the other face. Okay. Similarly, the stresses, the shear stresses, I could draw with another color. Okay. So this is the starting point. So I would represent that with some narrow mark. Okay. Okay. So similarly, you can imagine this face also having such forces. Okay. So I just wanted to write how the expansion will look like. Okay. So I'm concerned about the different axes now. Okay, because I need the forces in the various axes. So let me think about only one particular force component that is in the x direction. Okay, force in the x direction. So all the equations will follow suit. It will be similar to it. So this is why I want to write only in one direction. Okay, you can see that all the three axes are important, but I will write only one direction. So if you write this is equal to mass into acceleration, the mass of the element is known. Acceleration has to be found out with the change in velocity. Okay, and this is equivalent to the force acting. It is a summation of all the forces in net forces in the x direction is what you have to find. Okay, so the notation will go accordingly. So let me say that this fluid element is surrounded by other fluid elements. So it is under pressure. Okay, it is under pressure from the surrounding fluid elements. So that also have to be drawn. Okay, so let me draw that also. Okay, so here this is subjected to pressure from the surrounding fluid element. Similarly, you can imagine pressure being acting on all faces from the surrounding fluid elements. Okay, so let me name this as P, and the area would be, I can see here, this is dy. Okay, and this is dz. Okay. And this is dx. So it is very easy to find the area now. We can denote like this. This pressure is acting from the surrounding fluid is acting on this face. So it would be so dx into sorry dy into dz. This would be the area. Okay. So on the other face, on the equal and opposite face, on the opposite face of the fluid element, we can go adding the elementary change in pressure according to the Taylor series expansion, as I told you. Okay, so you get it through a Taylor series expansion. This is what I already explained. If you have a function at a point, you can get the function at another point and the point f2 based on Taylor series expansion. The value of the function with respect to the change in position with respect to delta x divided by 1 factorial plus the second derivative of the function. So you see that whatever you learned earlier is coming handy now in detailing the physics. Okay, the two factorials. So I told you for higher, smaller delta x, you can neglect this part. You can neglect the higher order terms. You can set this to 0. And this is the only thing that would come to your picture, even if you want to find one function with respect to another in continuum. Okay. Okay, so here F1 being the force here on one side, F2 is the force that you're evaluating on opposite side, which is separated by distance dx. So I can follow the same notation as I told you in the Taylor series expansion. Instead of F1, I can put P. Instead of the pressure variation, function variation with respect to space, I can put dou P by dou X. Instead of delta X, I can put delta X here. So this is how you got the pressure on the opposite phase as P plus dou P by dou X into delta X. So this sort of mathematical expansion is used in most of the physics, whether it is solid mechanics or fluid mechanics. You can see this sort of expansion when there is a continuity in function. Okay, so this is a technique that we use in engineering physics. Okay. Now, this gives you pressure, and now you have to multiply with the area, which is again dy by dx, which will give you the pressure force on one side. Okay, so it is acting normally from all the surrounding elements to the fluid element, so compressing it. Okay. Similarly, if you imagine this part, this I don't have enough space, right? So I'll just take it out and write. This is toe. So let me write this one. The green colored one is actually toe yx with our notation. So this is the stress. This is acting on the elemental area dx dz. Okay, dx dz. So dx dz. This is the area on which it is acting. So this would be separated by dy distance. Okay, this would be separated by dy by distance, dy distance. So I can just go on the Taylor series expansion again, plus the dou cho by dou phi into delta y. So this would be give the incremental stress on the opposite phase. Into the area again is the same dx dz. Okay, somebody's trying to join. I'll admit them. Okay. Similarly, this part of the stress, which is to xx on one side, okay, and the area on which it is acting is dy dz. Okay, so on the other side, it would be again the expansion would be based on Taylor series expansion. Okay, delta x, okay, and then the area dy dz. So I am just writing only for fx. Okay, I am writing only the stresses which will contribute to fx. This is why I am not considering all the others presently, because additionally, if you want to write the force equations in the other directions, you have to do that on your own. Okay, and now this I am writing only for one component of force. Okay, so you see here, these are the forces which will cause the motion in the x direction alone. Okay, this will contribute to fx alone. Okay, so if you write this equation as the net, so with this I write the net force that is acting on the x direction, net force in x direction. Okay, so I get f of x, f suffix x is equal, so p minus p plus dou p by dou x. Okay, don't get worried, because this is important to know some aspect of the Navier-Stokes equation that you will develop later, and also the convection diffusion equation that you will use for your numerical schemes. This is why I am discussing it. Don't worry. Okay, you need not by heart this order, but you just understand how it came. Okay, how it came to this form. Then plus, okay, to xx plus dou 2 xx divided by dou x into dx. Okay. This is again minus 2xx, and again it goes to, okay, so and so, okay, so and so you can write all this, okay, I'll either write that the one also, the other one also, so that we can complete one and discuss based on that. Now 2yx plus dou 2yx divided by dou y into dy minus dou 2yx, again acting on that area, dx dz, okay, and then additionally last term dou zx plus dou 2zx divided by dou z into dz minus tau zx, which is acting on the area dx dy. So you see that the net force in x direction alone is contributed by the forces which is acting on either faces of the cube, and that two taken in the direction of x alone. Okay, so you can see that this part and this part get cancelled. You can see that this and this get cancelled, and this gets cancelled, and this gets cancelled, this and this gets cancelled. Ultimately, you are left with f of x, okay, is equal to minus dou p by dou x. Okay. Then dx, dy, dz is common for all. So I will just go on writing the other terms. Okay, first, I'll write the other terms. Plus dou 2 by x divided by dou y divided by dou 2 zx divided by dou z. And this is uh, into dx, dy, dz, which is common. Okay, it's a very important finding. You see that on the left hand side you have Newton, and you have Newton on the other side, pressure into this pressure, gradient of pressure into volume, which use again Newton. Okay, Newton per meter into meter cube, Newton per meter square, Newton per meter cube into meter cube. That is Newton again on the right hand side. So this is force equation. Okay, so you can take this dou x, dou y, dou z to the here underneath. Okay, so you can see force per unit volume. So somebody is trying to join me. Okay. So here at the end we get force per unit volume. Force per unit volume. So force per unit volume. Okay, so Fx per unit volume is equal. Okay, so you get dou p by dou x minus dou p by dou x plus dou tau xx by dou x plus dou tau yx divided by dou y plus dou tau zx divided by dou z. Okay. So let me think. Additionally to this, okay. Additionally to this. So additionally to this, let me say that there is some magnetic field force which is pushing this in this direction, or some body force of some nature which is pushing in this direction. And by definition of body force, it has to act throughout the entire body, entire volume of the body, without any preference. So it has to act through the entire body. As I told you, gravitational force acts through their entire body without any preference that it is your head or it is your leg or it is your hand. It acts throughout your body without any preference. It acts through the entire volume. So here, if you see, I can say that if the element is to move in this direction, and I say that body force is influencing it, so let me say it is in the magnetic field, uh, or it is under a gravitational field, whatever it is. Some field force is acting in the x direction. Some field force is acting in the x direction. So let me write this as body force. To avoid confusion, let me write this as body force. Don't be surprised with the notations. I'm writing the notations because it is usually followed in most of the literature on textbooks. So the body force in the x direction. So let me say that the body force in this x direction is acting. Okay, additionally, and you can imagine the body force to be something like a magnetic field or gravitational field, which is prompting it to move in the x direction. Additionally to all these stresses, which is helping to move. So in that case, I can add to this fx. I can add the body force also. Okay, so I can add the body force also, which is trying to help to move it in the x direction. Okay, the body force. Okay, so I just wanted to include this here, the body force, which is causing the motion in the x direction. So this, the shear stress, normal stress components forces additionally to body force. So this is the contribution coming from surface force. The contribution coming from surface force. And this part is the body force contribution. So only thing is that to make it the unit balancing to Newton per meter cube, okay, here we should consider the small letter f suffix bx to be Newton per meter cube. So body force per unit volume of the fluid element. So that way you have to think about it. When you substitute the value as the source, you have to first find the value of the force and you have to divide it by the volume to make the units correct. Okay, so just don't directly put the source term in the Newton as a Newton. It has to substitute Newton per meter cube. So I'll just write it for your convenience for you to remember. Okay, it has to be substituted as Newton per meter cube. Okay, now you see this is a very famous relation. Okay, this is a very famous relation. You see here what is given on the left hand side. This is force per unit volume. So force is nothing but change in momentum, and you know the total change in momentum is actually the d by dt of it. Okay, so here it is a kilogram per meter cube into meter per second. Okay, per second divided by time. Okay, per second. So this is kilogram meter per second square. Kilogram meter. So this is Newton. Newton, and on the bottom you have per meter cube. So this is basically the same unit that we are discussing. Okay, Newton per meter cube. This is change in momentum, total change in momentum. So I told you the total derivative comes as a part of the control mass approach, and this is tracking the total change of momentum, total change in momentum of fluid element as per control mass approach. So this is rho u by dou t. How rho u became Newton per meter cube? I have discussed this by balancing the unit. You can see that m into v or m into u. You can say that is momentum. Okay, momentum per change of momentum divided by time. So you will get acceleration. So change in momentum divided by time will give you force, and the density term ensures that underneath it there is a volume component. So it becomes kilogram meter per second square divided by meter cube, that is Newton per meter cube. So the one you are tracking on the left hand side is nothing but dou rho u by dou t. And on the right hand side you have this, okay. Akash sir, കുഴപ്പമില്ല. I was just having a problem with the computer. I cleared it. കുഴപ്പമില്ല. Check it.
Okay, sir.
Okay, thank you. So here on the right hand side, you have, you can write instead of this, dou P by dou X, you can write gradient of pressure with the notation I already told you. This is gradient of pressure in the X direction. Okay. Additionally, you see here you have, are you all on the other side? Are you all listening to me?
Yes, sir. Yes, sir.
Are you able to follow what I'm trying to tell you? Guys,
Yes, sir.
are you able to follow? Okay. Yes.
Yes,
Somebody
sir.
is replying yes. Okay. Okay. So I will not discuss anything which is not important to you. Okay. I will only discuss which are important to you. Because later, when you come across equations and when you have to select some numerical schemes, you should understand why it has been selected. So this sort of information will help you. Okay, don't worry. Don't worry about the derivation and all. So here you see the left hand side is this. On the right hand side, instead of the partial derivation, the dou P by dou X, I have just plainly written gradient of pressure. Only the component of X is taken here. So if you see here gradient of pressure, it has got all the components, dou P by dou X, which is in, now it's a vector actually, right? It's a vector. So plus then you have dou P by dou Y, which is in the J direction, and plus the pressure variation in Z direction. So you have all this. So I have written only the X component, which is a scalar, which means that I have taken only this part. Okay, this is the scalar part of the gradient of pressure. So similarly, if you want to write the other momentum Fy, you will have this to include this. So it will be gradient of pressure, the Y component of it. So this part would be gradient of pressure, the scalar Z component of it. Sorry, guys. So this, the Z component of it. So just understand that I have taken only the X component of it, which is a scalar. So I can write, this is a scalar equation. So I can write, I can take the scalar part of it, which is only in the X direction. I included it. Oh, I missed some. Okay. 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 Similarly, okay, I lost some information because. Okay. Because of this pen, I lost some information. So I filled them out. Okay. Now this part I have to write. And closely observing this shear stress equation, you have an equation for shear stress based on Newtonian fluids or non-Newtonian fluids. You can relate shear stress and viscosity and gradient of velocity. Okay. So you can relate always this. Okay, we have Newton's equation, viscosity, law of viscosity, or people are still joining. So Newton's law of viscosity tells you that the shear stress and rate of shear strain, okay, can be related with an equation. They are always proportional for Newtonian fluids, and they can be related through an equation when you include the proportionality constant as term called viscosity. So viscosity is basically the term which helps to connect shear stress with shear strain. Okay, so in Newtonian fluids they are related proportionately. So in non-Newtonian fluids, we have a nonlinear relation, whether it is rheopectic, thixotropic, non-Newtonian fluids. We have variation of viscosity and shear stress, which is non-linear. Okay, so I'll not go into that. But still, there is a relation between shear stress and rate of shear strain through some exponent function or some constants appearing in the gradient value. Okay, but for Newtonian fluids, you can say that they are directly related through an equation where you can use the proportionality constant, which is called as viscosity. So viscosity actually connects shear stress with the rate of shear strain. You can do experiments to find this, if the fluid is viscous or not, Newtonian or not. Okay, most of our fluids are Newtonian in concentration, or if it is not, it will be informed to you before the start of working out a problem. Or if you want to work with some specific biological fluids, blood or human body fluids, okay, then you have to consider it to be non-Newtonian. You cannot directly use this relation. Okay, yeah, it goes by an exponential function. Okay, okay, fine. Anyways, let us consider for the time being, this is a Newtonian fluid which you are writing the equation. Anyways, so here you see the stress part, which is it is related with viscosity. It is related with rate of shear strain in this fashion. Okay. Okay. So here instead of normal stress, I should write this for shear stress. This is actually normal stress. I don't require that here. So let me erase this. The one I have written is for shear stress. Okay. Okay. So you see here, that sort of substitution can be done here. So if you want to take derivative, so if this is the case, what is the derivative of this stress? Okay, then I have to apply the derivative here also. I have to take differentiate this also. So if viscosity is a constant, okay, so if I consider viscosity being a constant, if it is not, it should be inside the derivation differentiation. Good. So if it is constant, I can take it out. Then it looks like dou square u by dou y square. Okay, dou tau yx divided by dou y. The term here. Okay, the term here is actually looking like mu into dou square u by dou y square. Okay. Okay. So similarly, you can imagine all the shear stress components, which are influencing the other parameters. Okay. So here it would be dou u by dou x. Okay. So here it would be, I have to erase this. Okay. So I'll take. So here dou by dou x of tau xx, which is equal to dou by dou x of mu dou u by dou x. Okay. So here it is again mu dou square u by dou x square. This is the expansion for this term. So here you see that ultimately, let me rewrite this equation in another page. It gives the change in momentum, the total change in momentum is going to be, so I have x momentum equation, this is called x momentum equation. So I can similarly write y momentum z momentum equation. This is going to be equal to the scalar component of pressure gradient in the x direction plus mu being common, all the other terms now appear as dou square u by dou x square plus dou square u dou y square plus dou square u by dou z square plus the body force component, which is in the x direction. And you see this is nothing but Laplacian of u. Then mu is appearing here, so I have to write mu into Laplacian, and then you have the pressure gradient in this direction plus body force component. I'll tell you one easy way to remember this. Okay, I'll tell you an easy way to remember this. This is a final equation. Okay, I'll tell you an easy way to remember this. people struggle trying to remember this equation or trying to relate the physics of this equation. I'll tell you, this is very easy to remember. So this part is the Laplacian, okay, which goes here, and this comes here. Okay. So just physically imagine it. Just this equation. This is called as x momentum equation. This is a part of Navier-Stokes equation. If you can say, so similarly, you can write the other components also. So the other components. Okay. So the y momentum equation. The y momentum equation. You can write the gradient of pressure in the y direction. Akash. I lost information. I'm sorry, I lost some information. I'll write it again. Sometimes they can use me. So I just give, you can write it fast, no problem. The y momentum equation. So just take the scalar part of it. Okay. Body force component in y direction. Is that momentum equation? See? Together, three equations. So this is x momentum, this is y momentum, and this is z momentum equation. It is called. They are force equations, force per unit volume equations, and together these equations are called as Navier-Stokes equation in fluid mechanics or fluid dynamics. Navier-Stokes equations. Okay. So basically, this is the concept of developing Navier-Stokes equation. And if you want to remember this, is a very easy way to remember it. It says that force, and please take it, obviously it is force per unit volume, is contributed by gradient in pressure. You should read like that. If you read the equation, it is very easy to remember. If you try to learn with notations, it is very difficult. You should read the equation. Gradient in pressure in the same direction. So whether it is x, y, or z, same plus. And you see this is Laplacian of velocity multiplied with viscosity, which came from viscous forces. Okay, which is actually, you saw that this came from viscous forces. Okay, it is connected with Newton's law of viscosity. It came from viscous forces. So basically, that part is viscous forces. So effect of viscosity, right? Effect of viscous forces. Akash. Effect of viscous forces plus additionally effect of body force. So such a simple equation which makes sense physically. If there is a motion for fluid element, or if there is fluid motion, it has to be governed by pressure gradient, it has to be governed by viscous forces, and it has to be governed by body forces in the direction. So it's very easy to remember that. Excuse me, welcome just now. Sorry, guys. The power was running low. So, did you get it, guys? Did you get what I'm trying to tell you, everyone?
Yes, sir.
Is it okay?
Yes, sir.
Okay. So, please try to relate physically what happens with fluid and motion and how these equations can be simply easily remembered. And when you see an equation which is showing Laplacian of velocity multiplied with viscosity, don't be surprised. It is just showing viscous forces. Okay. So you should not be surprised or afraid that looking at that equation, what does it mean? It just means that it is a viscous force. Okay. So when you see del P or gradient P, you should not be worried. You should think that, okay, pressure gradient is acting on that body. So if there is something like a source term is written, and it says that F suffix B, you just understand it's a gravitational or magnetic field force. So if you start thinking like that, fluid mechanic equations start making shapes in front of your eyes, and you're not surprised to see equations, and you'll not be worried. I have to remember this. Okay. So I hope it is clear. So this is how it will be developed. Okay. Similarly, the last set of equation, I will not write any derivation, but I will only mention which is very important to you. Okay, because I need to move on. Okay, I need to move on. So I'm just going to write only the last set of equation. So I will just retain this. I will come back to this page. So I will have to retain this. So I'll go to the last set of equations, that is energy equation. So conservation of energy it is. So applying the same physics. So just for your convenience, I'll only draw one picture to show what is important.
Sir,
Other
I have
than what
one
we.
question regarding Navier-Stokes equation.
Sorry, can you repeat again?
Sir, I have one question regarding Navier-Stokes equation.
Yes, please.
Sir, you have written that d rho u by dt is equal to pressure gradient term plus viscosity term and body force. Sir,
Yes.
I have seen in one literature it's one additional term dy dx mu plus lambda duk by dxk. So what is signifies this lambda? What is the significance of?
Yeah. Yes, it's good that you asked. I was just trying to skip that portion because I thought that you might not be interested to learn that much detail. Okay, I'll
Yes.
come to that.
Okay.
Okay. So here, wow, then I have to explain a little bit more.
Okay.
Okay. So if
Yes.
you're interested, I will explain that to you. So for Newtonian fluids, okay, this is applicable for Newtonian fluids. Okay. There was a scientist known as Stokes. Okay. For Stokes, you can see there is entire flow regime under his name, Stokes flow regime. Okay. He worked really on highly viscous fluids. Okay. So for him, the viscosity, this term mu was very important to him for his studies. Okay. So, and there is an important category of fluid physics, Stokes flow regime, which is very important engineering applications. You want to really go into colloidal suspensions, flow of suspended particles, droplets moving through Eulerian fluid field. Stokes flow regime is the answer for you. So that scientist, he was working in 17th century. Stokes was working in 17th century. Isaac Newton was working in 17th century to give details on Newtonian fluids. Later, when Stokes started working for his flow regime calculations, then he understood that he could establish this relation for what Newton gave relation for with shear stress in terms of lambda. Okay, I will come to that. Lambda is divergence of velocity into divergence of velocity plus 2 times mu. Okay, and then the gradient of velocity. So he could understand for the Newtonian viscosity, Newtonian shear stress could be related for Newtonian fluids. This could be related to lambda into divergence of velocity plus 2 mu dou u by dou x. Okay, through his experiments. And here lambda he called as bulk viscosity coefficient. Lambda he called as bulk viscosity coefficient. okay, of the fluid. You already know what is bulk, compressibility coefficient. You know such terms, right? Here, lambda he called as bulk viscosity coefficient. Okay, and for him, from his experiments, he understood that lambda was minus 2 by 3 times the viscosity for Newtonian fluids. So there is no proof why it is minus 2 by 3 mu. Okay, this is without proof. But till date, nobody has counter proved that it is not. Okay, so till date, nobody has counter proved this not. And this value, lambda, which he called as bulk viscosity coefficients, actually relates the Newtonian viscosity shear stress tau xx in terms of the term he established, bulk viscosity coefficient, through the velocity gradient as a product of it, plus mu2 mu dou u by dou x. So you can see the one earlier one, the equation you see, you have dou tau xx by dou x. You could replace this. You could replace this tau xx with what Stokes proposed. The value that Stokes proposed. You can take this value and substitute it here. So now this equation will completely look different, and it will appear in the terms of the bulk viscosity coefficient, which Stokes proposed, for which the value is minus 2 by 3 mu for a Newtonian fluid. Okay, this is from his experiments. He came to this value through his experiments, but there is no proof for it. Why it is that value? Is it okay?
Yes, sir. Yes, sir.
Okay. So in some textbooks, if you see some textbooks for which the Stokes flow regime is discussed, you may see that bulk viscosity coefficient is the way in which the entire Navier-Stokes equation would be written. Or in other ways also, for Newtonian fluids, you can substitute for tau xx in terms of this, and you can get the relation that you are asking for. And it will be more lengthier equation, because you see here the same tau xx would have include all these terms. So you see that there will be a lot of additional terms which is coming then.
Yes, sir.
Okay. So if it is important that you want to study that equation, or in your physics you want to model something like Stokes, which is viscosity is of prime importance, and if you have some bulk viscosity coefficient available from literature or so, you can use that. You can use that equation. Is it okay?
Yes, sir. Now absolutely fine.
Okay, fine.
Thank you, sir.
So Navier-Stokes equation, I see that it can be written in many different forms. Okay, I am not only discussing very little. There can be many different ways you can write it. So sometimes you can get lost writing that equation, okay, in different forms. So here, while discussing energy equation, only thing I want to discuss with you is the concept of conduction, okay? Because this is very easy. So here, energy equation is basically energy conservation equation. Energy conservation equation. So basically, just like we wrote momentum conservation equation. So here, you see here, we took a fluid element which is under motion, and then we applied all the possible stresses that can come, which will contribute motion in the x direction. Similarly, I go writing all this forces, which is all sort of energy that can penetrate this body. Okay, so here basically the energy in the sense that okay, I'll just go in one thing I will explain. Okay, here you see that there is a shear stress, there is a shear force. So shear force into the displacement. Okay, so that would be Newton meter. This is joules. Okay, per time t per time. This would be watts. Okay, joules per second. So this is in second, and this Newton meter per second. So this is joules per second. This is watt. This is a unit of energy. Okay, so you can actually calculate shear force because you already know shear stress multiplied with area would give you shear force. The displacement you can multiply with the displacement. Okay, that is affected on this phase. Similarly, you can think about having force and displacement in all the phases. That will contribute to the energies of energy interaction between the on the spaces of the fluid. So additionally, you have the internal energy of it, okay, the internal energy of it, uh, and then additionally you have the fluid is moving, okay, the fluid is moving with some the fluid particle is moving with some velocity, so you have kinetic energy associated with it. This is internal energy. Then you have kinetic energy. Then you have energy coming from force interactions on spaces. And very importantly, the one which I want to mention you now, which will not be detailed in many of the classes, but I want to for you to understand this because it's very important. The energy interaction from the surrounding medium to the fluid element through its phases, okay, through its phases in the form of conduction, okay, through the form of conduction. And this is basically dependent on the conductivity of the element. So this component will be dependent on the conductivity of the element, okay, the fluid particle. So you see here, for when you think about conductivity, immediately the thing that comes to your mind is a solid, okay. But please be aware, conductivity is as important in fluid as it is important in solids, okay. So I'll give you one example. I'll, I'll give you one example why it is very important. So this will be the last section for today. I'll just show answers and then I'll just wind up for today's class. I can take another 10 minutes. Is it okay with you guys?
Okay,
Is
sir.
it okay? Anybody has a problem? I can stop now.
No, sir. No, sir. No problem.
So only very less number of participants are there today. 48. We have 63 participants registered. I think people have started losing interest. Okay, anyways. So let us think about energy interaction. Okay, energy interaction. Energy from a body. Okay, let it be a solid body. And I have some fluid here. This is for an example. Don't think this is the only way it is interacting. Okay, I just want to give an example to make you think how important it is. This is fluid. Okay, this is fluid, and this is solid. And you're trying to impart energy from the solid to fluid. You're trying to impart energy from solid to fluid. So at the first layer, you see there is a presence of fluid particle which is attached to the solid walls. Okay, I will draw that fluid particle big enough. It's not as big as what I'm trying to draw now, but you can think that this is a big fluid particle. And you see that the first interaction it is having with the energy imparting surface is conduction. There is no doubt about that. The first has to be conduction. Then only the convection phenomena happens. Okay. Okay. The bulk motion, the fluid heat transfer through bulk motion, convection will happen only later. The first is conduction. So if you go inspect any energy transfer at its elementary level, conduction is the phenomenon. Whether you have received energy through radiation, whether you have received energy through convection, whatever mode of heat transfer, but the energy has to come through the phase by conduction. So this is why in the energy equation you will see K, conduction heat transfer coefficient, rather than anything else in the equation. For a fluid element in concern, it has to be through conduction that the energy has to come in. So this is why this equation, the energy equation, I'll write it in detailed form. So the energy equation with all these notations which I have used: internal energy E, velocity which is contributing kinetic energy, vector V, when shear forces, which already you know that is tau xx or tau xy into the area, into displacement that is happening. Okay. Uh, so displacement would mean dou u into t or something like that. So it goes on like that. Okay. So here, with all these considerations, So it's now okay. Let me write and complete. I have to take it up further. Waste time. So with this notations, okay, which I already explained, this goes to a big equation, energy equation, plus dou by dou x of k, the conductivity, dou t by dou x, plus, okay, dou y by dou x, dou y, k dou t by dou y, plus dou by dou z, k dou t by dou z. Okay, now also the pressure force is trying to move it, so there is a force coming from there, then the force into displacement that will give you additional work or energy from that side, the pressure forces. So that appears plus some other terms. Okay, the bulk viscosity coefficient, if you can include, so it will also come. So I will not write all those things. Okay, I'll just add only the. It's okay. I'll just write only what is relevant. I'll wind up within 10 minutes. Don't worry, guys. Okay. Mu into 2 times dou u by dou x. So it's elaborate. It's very elaborate. Plus 2 times dou v by dou y whole square. Plus so big equation. Okay. So I can get this equation anywhere. Plus, don't be worried because it involves conductivity. Why conductivity came? That sort of equations. That sort of things I have already answered. Why it came. Okay. So it becomes a big equation with so many terms included. So if you look it carefully, I wanted to tell you something. This is why I started explaining this. Otherwise, I would not have come to this. Okay. I want to explain this before we leave. Okay. I want to explain this before we leave. So if you observe this carefully, this equation also carefully, this is actually total derivative of energy. That is the how internal energy changed, how kinetic energy changed. Okay, so this is total energy change. Okay, so I will write total energy change. Okay, so only one component. If I want to write only one component, I will write the u component only. Okay. So if you want to write further components, I can do that. I will write only one component. Let me write E plus V square by 2. So at the end, it looks like this. Okay, I'll just write without any explanation. I'll write d by dt, the total energy change. Then this is actually the energy that is crossing the boundaries. Okay, the internal heat, not crossing the boundaries. This is internal heat generation. So if there is any internal heat generation, you can include that also. Plus, I'll just write dou by dou x of k dou t by dou x. So and so. Okay. Then some component becomes so my idea was to just tell you why some terms are important. So let me conclude this. Okay. Plus some terms with k dou t by dou x or simplification. So and so. Okay. So I was trying to relate this what you have already written. So you see here for the momentum change, you had the total change in momentum expressed in terms of gradient in pressure and viscosity force. So you can, if you want, you can write this part as I can write like this. Okay, mathematically it is possible to write this because del square is nothing but del dot grad of the scalar. Okay, so if you first find the gradient and then take dot product, then it should return the scalar, which is del square u, which is a scalar. You see? Okay, so the expansion is divergence of the gradient of the scalar, which is here, and this is the way you can write. Okay, if you want to write in that form. Similarly, you have some parameter here, which is dou by dou x into k dou t by dou x. So here it is the k dt by dx. You know, this is energy which is coming in through conduction, and you see the energy that is penetrated through conduction or transferred through conduction is called as diffusion heat transfer. Okay, so in heat and mass transfer, you might have learned the energy that is percolated or this is transferred by virtue of conduction is called as diffusion heat transfer. So this is again a diffusive term, the diffusive transfer of heat. Okay, so and this is showing again. So the gradient is so this is also a form of del dot grad of something. Okay, grad of temperature. Okay, you can see, and here you have just observe this equation carefully. See that it appears like diffusion, the divergence of k multiplied with gradient of temperature. Okay, so now this is returning a vector, and this is taking a dot product, and it returns a scalar, which is again this form. Dou by dou x, this is guaranteed by del dot, and k dou t by dou x is guaranteed by k grad t. So see how close these equations are. Here it says del dot grad u, and here it shows del dot k delta t. Both are diffusive terms. Okay, this is viscosity is also diffusive. Okay, viscosity is also diffusive. Similarly, uh, I said diffusive because it appears as a Laplacian. Okay, it's an elliptical equation, so it is a diffusion equation. So now here it says that it's again an elliptical equation, which is again a diffusive part, and it is a diffusion heat transfer. So what I am trying to tell you is that this right-hand side, it can be clubbed together to represent something like a divergence form. Okay, it can be represented as a divergence of some quantity. Okay, the right-hand side, it can be written as the divergence of some quantity. Okay, so I'll stop here. I'll continue tomorrow because I want to explain more on this. And this is actually leading to the convection diffusion equation. Okay, if you understand this clearly, you will understand why convection diffusion equation is that form, and also why some numerical scheme has to work in the way they work. Okay, so is it okay, guys? Do you want to see the software now?
Yes, sir.
Okay, so I'll just present the software for 5 minutes, and sorry. So here, I'll just wind up within 5 minutes showing the software. So please understand, just a concluding word. Concluding word. Please understand all those equations, whether it is the conservation of mass, whether it is conservation of momentum, whether it is conservation of energy. all these equations can be written in the form of divergence of some quantity. Here, divergence of the quantity which is taken is divergence of the gradient of velocity, which is actually viscosity part. Okay. Similarly, here you see that here it can be represented by divergence of the energy or the conduction heat transfer, which is given by k delta T by delta x, which usually appears in the Fourier heat conduction equation. We already know that. So this is again written in the form of divergence of the gradient of temperature. Okay. So you see that some relation on the right hand side represents this to be in the divergence part, which is very important for you to understand. Okay. So now I'll close this. I'll show the software. So the I will not prefer a particular software over the other because it depends on you what you'll use. But I am comfortable with using Fluent. You may download Fluent from ANSYS website. The release 20 R20 is available from audible to you. Am I audible to you guys?
Yes, sir.
The connection got disengaged. So I was telling you, you can download the software from ANSYS website. Release 20 is available, student version, which is valid for 1 year. Okay. So if your college has a licensed software, you can use that. Okay. So here, just I will show you a simple. I will first familiarize with you with the interface. Is it required? Do you want to get familiarized with the interface, or you already know about this?
Sir, I guess some students are there who don't know the interface.
Okay. Do you mind the others? Do you mind me explaining the interface to people? Others? This is beginners, so I think
No, sir.
it
No, sir,
should
you can
also be
explain,
very
sir.
streamed. Okay, fine. So only 45 are there. Many people have left. Okay, I'm really sorry, guys. It took some time.
Sir, you can explain the regarding interface.
Okay. Okay, I will explain. So here, usually the Fluent is now available. ANSYS is now available, and the release 20 R20 is available in the ANSYS website. Go to the ANSYS website, download it, and this is the one which I downloaded from the website. And you see here, you can go type here. ANSYS once it is installed, you can go type here workbench. Okay. You can type workbench. So you see here, it will show the workbench that is installed. Okay, you click on that. So it takes you to the workbench. Okay. So why it is called workbench? Because it can have multiple analysis systems. Okay. You can have multiple analysis systems in ANSYS workbench. So it's a multi-physics solver, which means that you can solve different physics together. You can club together different physics. You can solve different physics at the same time. Okay, so you can interlink one solution with the input to another physics. So it can be fluid structure interaction. It can be chemical fluid interaction. So many things are possible with this workbench. This is why it is called as a workbench. There's a lot of systems which is associatedly available. You can club together different systems. So usually, as a fluid mechanics, I am mostly working on. I usually work with software called as Fluent. Okay. So similarly, CFX, Polyflow, and all are fluid flow solvers. You can see fluid for solving fluid flow. They have different types of solvers available. So some people prefer CFX over Fluent. Some people prefer Polyflow for some simulations. So it depends how you have experience with, because each software will have a learning curve. You have to learn a bit on how the interface is done, how what they mean by some terms there. Okay, so it takes some time to get familiarized with the software. So some people already comfortable with CFX will continue using CFX. So please understand, ANSYS has bought many of the softwares or rival competitors during the time long over the years, and now all these are under ANSYS now. Okay, CFX and all are they were actually different software solutions. The ANSYS bought it, and they brought it under their workbench. Okay, so ANSYS had Fluent earlier. So when I double click ANSYS Fluent, it takes me to this window. Okay, so here you see that the window promises me, so several things can be done. I can draw the geometry, I can do a meshing, I can set up the physics, I can run the solution, I can see the results. This many things, this is guaranteed. And if you see here, this is what I already told you. For CFD, you require a grid generation, you require a discretization method, the conversion of LA to PD, PD to LA. Then you need a solver, you need results to be seen. Okay, this is the step which goes for answer, simulation. And the same steps are available here. You want to draw, you want to mesh, you want to do the solver, you want to see the solution, you want to post-process it. Okay, this goes in that order. So if you right-click the geometry, two different drawing softwares are available in ANSYS Fluent. Either you can draw in space clay, which is the default one, or you can draw in design modeler, which I am comfortable with. So I draw the geometry in design modeler. Okay, so I draw a geometry in design. So this is design modeler, which is used for drawing your physics. Okay, you want to model your physics because there are boundary conditions. There is physical boundaries which you want to see before assigning values. So to visualize things, you can draw it in a modeler. Okay, so now on the design modeler, this is the design modeler in a graphic user interface. In the design modeler, you have so many options available. Okay, so let us see what are the options available. So here you can, in the file section, you can have, you can export, import, load projects. Okay, you can import geometries. Okay, on the create side, you can create plane. You can do some math, geometrical operations like extrude, revolve, sweep. Okay, then blending, slicing. Then you can have some primitives which are already available geometries, primitive geometries. On the concept side, you can create lines from points, lines from sketches. So all geometry related things are available here, splitting, projection. So, and then in the unit section, you can switch units from meter to centimeter to millimeter, whichever is your preferred unit. And then in the view section, you can go by seeing different type of views are possible. If you want to see the edges, you want to see its wireframe. So different types of visualization. It's up to your comfort. Okay. Then you have a help. So wherever you are, you just press F1. It takes to the help that is for that particular screen. Okay, or particular command that is active there. Okay. So now on the bottom, you have so many options. You can save the file. You can take a picture and capture the picture and save it as a PNG file or JPG file. And here you have a select mode, which has see two different select modes: point selector or single select, box select. Okay. So if you select single select, if you select box select, you can just go and drag and select the entire thing. If you want to have single select, you can go pick individual components. Okay. So here another filter is available. Now it is like point, edge, face, and body select. So here if you want to select a point, you can select. If you want to select the edge, you have to go and select. If you want to select the face, you can take this and otherwise, if it is in face mode and you want to select this edge, it is not possible. It will only select face. So some people struggle selecting geometries, but they are not able to understand why it is not highlighted. The reason is that you have not selected which one to be selected. So body, okay. So it depends which one is active there. If it is not active, you have to go make it active. Then only the thing that is required will be selected. Okay, so this is very important. Even though it looks very trivial, people struggle not understanding why I'm not to select this point. That's because of the reason it is not active. That's it. So then this is, you can rotate the left mouse, you can rotate. Okay, here you can pan it. Okay, you can move this body here and there. Here you can go zoom. Okay, so here you can zoom to a point. So if this is fitting to the screen, and this is magnifier window magnifier. Okay, so it magnifies where you are pointing. Okay, uh, so I'll fit to window. And then this is a section plane. I can just section it. I can just delete. Sometimes you are interested to see what is inside after drawing. So you can take this section plane. Once you select this, this automatically comes on the lower bottom left hand side. And section plane, if it is deselected, okay, you can delete it if you don't want it. Okay, so you can right click and delete it if you want. So if there is a section plane, you can, if you don't want, you can delete it so that it will return to the original. Okay. So different display models, solid display plane should be displayed or not. If you want to activate the plane, sometimes you are interested where is the normal. Okay, then you have to activate the plane tool. So it will show which is the normal, which is the. So the left mouse button, and you can just rotate it at your convenience. And this is like look at window. So it will take you to the original active drawing plane. So here I have drawn the sketch in XY plane. Okay. So the XY plane is on which I am active. So it will go to the, so if it is in this disoriented condition, I want to see which is the plane on which the sketch is lying. You can just click it. It will orient me directly to that. So this much I have explained. I have explained the workbench, why there are so many analysis systems, what all things can be done. I have explained Fluent is the one which is of interest because this is one which is commonly used by fluid mechanics people. Okay, you can even work with CFX if you want. When you double click, it takes to this window, and on right click of the geometry, you can select space claim or design modeler. I have activated design modeler. So in the design modeler, you can draw, and there are tools which will help you draw it. We discuss what is there in file. We discuss what is there in create. We discuss what is there in concept. We'll come to all those things. Okay, there are so many. And here we discuss the second row. And then we discuss what is meant by single select, box select. We discuss what is the selection filters, why they are required. We discuss all these tools here, available here. Up to here we have discussed. Is it okay for today? It is 6:30 now. Now 43 people are there. Okay.
Sir,
Yes, tell me.
sir, this software does it include the CFD part as well, or that software is separate?
Actually, I didn't get you. Can you repeat again?
Sir, this software is having CFD part as well, or only this designing is there? 3D modeling is there?
Yes. This is workbench. Workbench means you can draw, mesh, solve the CFD, whatever physics you want to solve. You can see the result. It is available in one roof. This is why it is called as workbench.
All right, sir.
So if you want to work on Fluent, you just click on Fluent, double click on Fluent. It will open an interface where you can work with Fluent. And there you can do all these things which I told you. But if you just want to take individual components, you can just open the individual component system. And then you can click the one which is only required. If you want to draw just the geometry, you can just click. It will open only geometry. Okay. So if you want to just mesh, you can just double click mesh. So in that case, you have to provide a geometry to the mesh. Like this, you have to provide. Can you see that?
Yes, sir.
So if you want to do analysis separately and Fluent is only standalone, you are taking, then you have to do the all those previous steps you have to do individually, geometry, mesh, setup, everything has to do. And then you have to connect it by dragging and dropping into the respective one. So it will be connected. So you can do that if you want to do standalone operations, because some operations already done and you want to connect the result of that to the new one. Then you don't you have all the previous things that you have to go by. So you can just start from where you want the component to be placed. Okay. So individual components can also be placed, and you can just drag and drop the connection between components so that they will work together. Or otherwise, you want to do a complete analysis starting from drawing, analysis, everything. Then you have to just double click on it. So it will open up all the possibilities. If you don't want, you can delete it. So in the left hand button, you can just go and delete if you don't want. You can delete it. You can go on deleting if you don't want. So it is just getting familiarized with the interface. If you want, you can just please download the software. Okay, please download the software from ANSYS site and practice it. You just click different buttons and see what they offer. Okay, these things. Just get familiarized. It is not big deal. Is it okay? Is it okay for today?
Okay, sir.
Okay, so
Okay,
I'll
sir.
just wind up telling the essence of what we have discussed. We discussed the governing laws other than mass conservation. We also discussed that how governing laws can be written in the diffusion, the divergence form of equation, how they represent the divergence form equation, and we'll come to see why divergence form of equation is important to us. We'll come to that, and we also discussed how the software interface looks like, and some of the buttons we discussed. Okay, thank you. Thank you, guys. We'll meet tomorrow. Yes.
Sir, we know that
Yes.
the conservation, mass conservation and momentum conservation, and another one is energy conservation. So suppose
Yeah.
I want to find out the parameter, suppose velocity and pressure. Then I need to combine both conservation equation and momentum equation, or I need to
Yes,
add.
yes. All these things go together. If you want to solve a fluid flow problem, mass conservation and momentum conservation has to be solved together.
Okay, that's mean the coupled. Both are coupled. Okay.
Yes. The result will always be. The result is always a coupled one, in the sense that the mass conservation equation, you have the velocity field coming from there, and in the momentum conservation equation, you have the pressure and velocity fields both. So the information has to come from the velocity field, and the pressure field has to get updated accordingly. Similarly, the pressure field has to update the velocity field. So they are all together. They have to find a solution together. So this is why the iterative mode of solution is required in CFD. You have to reach a state where they all agree together. It is not like one person agreeing and another person disagreeing. Everybody has to agree to a common result.
Okay, sir. And that
Okay,
means
till then people agree to a common result. They all go on iterating. Okay, finding the solution. This is why it is important. And also, if there is no energy interaction, by energy I mean temperature gradients or heat transfer modes, there is no availability of that information, or if that information is not important, then you can just ignore the energy equation.
okay.
So if the flow is taking place at room temperature, no energy interaction is happening, in that case you can just neglect the energy equation from the solver. But you cannot neglect the flow the mass and moment equations, because that is actually dictating the flow physics.
Okay, sir.
Is it okay?
Okay, sir.
Guys, this is level 1. Please understand, this is level 1. In other levels, we take up to different, all the things that you are discussing. We'll go step by step. Okay.